Welcome to the video lesson for section 3.1. Today we're going to talk about exponential functions. We're going to talk about the graphs, the properties, and some of the behaviors. Let's get started. To begin with, we have the general form for an exponential function. So the exponential function with base a is defined as f of x is equal to a to the x. The important thing to notice here is that we have a variable as our exponent, which is different than some of the other functions we've had. We also want to note that a has to be greater than 0 and a cannot equal 1. If it is actually 1, then we no longer have an exponential function, but just a horizontal. For instance, two different examples, we have f of x is equal to 3 to the x or 0.5 to the x. Those are both different examples of what an exponential function might look like. Here we have the graph of f of x is equal to a to the x, specifically when a is greater than 1. And we have a couple different properties we want to make sure that we note. To begin with, we can see the domain is going to be all real numbers, and that is because the graph continues all the way from left to right, and it just keeps on going. For our range, notice it's a little different than the domain. The range is actually going to be from 0 to infinity, and that is because you can see down the bottom we have a horizontal asymptote of y equals 0. So on the left side, the graph is going to start to flatten out. It's going to keep going, flatten out, approach 0, but never actually touch it. Whereas on the right side, it's going to keep going. And we're going to call this an exponential growth model because as we go from left to right, the graph is actually increasing. One last thing to point out is for our original function, we do have an intercept of 0, 1, and this is a y-intercept. Here we have the graph of f of x equals a to the x, where a is going to be between 0 and 1, and notice we have a different curve here. Instead of increasing, our function is now going to be decreasing. Even though it's decreasing, though, we have the same properties for our domain. Again, it's still going to be negative infinity to positive infinity. Your range is also going to stay the same. Your range is going to be from 0 to infinity. We also have our horizontal asymptote of y equals 0, and we have the same intercept of 0 and 1. So nothing has changed here. And one thing to note, for your exponential functions, you will always have a domain of negative infinity to positive infinity, no matter what the function has been changed to be, as long as it is exponential. Let's go ahead and look at the transformations for our functions. I call this first variable b, but it's just a generic variable and it talks about the vertical shifts up or down for our functions. So we have the initial function of f of x equal to 2 to the x, and we're going to explore how changing the function to be either 2 to the x plus 1 or 2 to the x minus 1 is going to change the function, and also what that could potentially do to our domain or our range of the function. Let's go ahead and compare them. All right, for our first comparison, we're going to be looking at 2 to the x plus 1 and comparing that to regular 2 to the x. The first thing we want to point out is our black function, the new one, has been shifted up. And notice because it's shifted up, we have a different horizontal asymptote of y equals 1. We also have a different intercept, which in this case would be 0 and 2. When we look at this function and we want to discuss the domain, our domain has not changed, and I mentioned before that it never will. It's always going to be negative infinity to positive infinity. If you look at your range, though, the whole function has been shifted up 1, and we can see that because of the plus 1 here, and also your horizontal asymptote being up 1. So now, instead of starting at 0, our range is going to go from 1 to infinity. So now that we've discussed all the features, let's go ahead and just examine a relationship here. Notice that the initial function was 2 to the x. Our shift is going to be plus 1, and that has changed your asymptote to be y equals 1, and also changed your range to be 1. And that's not a coincidence. Those numbers are always going to be interrelated with each other. If we go ahead and look at our next example, we're now going to be comparing 2 to the x minus 1 with our initial function. So the blue function is 2 to the x. We have a shift of minus 1, which is going to move the entire function down. And notice your black function is that 2 to the x minus 1, which is down 1. Your asymptote now is going to be at y equals negative 1 instead of at 0. Your intercept also got moved down as well. We can see that, again, your domain has not changed. So your domain is still going to be negative infinity to positive infinity. But now for your range, because of that shift down, we're going to be going from negative 1 to positive infinity. And again, we can see the relationship here. You have your asymptote, which is at y equals negative 1. You have your range, which starts at negative 1. And we can see the vertical shift is down negative 1. For our x variable, it does have a very specific effect on your graph. If we look at our two functions, we have the original function, which is our blue one. That is a growth function. And then for our new function, which is now g of x equals 2 to the negative x, we can see that it is our black function which has been reflected across your y-axis. So if I were to change my x variable and make it negative, and look at the graph is going to be reflected across the x-axis. Another way we can describe it is because our original function was a growth function, by changing your variable to be negative, we now have a decay function. So it's going to change from growth to decay or from decay to growth, whatever the original function was, but we can also just say that it's reflected across the y-axis. The domain will stay the same and the range will stay the same if the only transformation is making a variable negative. For our next transformation, we're going to look at a variable that I call a, which is really just the value in front. Instead of having a positive 2 to the x, we have a negative 2 to the x. So by making the entire function negative, we can see that what we're going to have is a reflection across the x-axis. So my original function was a growth function, increasing from left to right. And then I would take that entire function, flip it over the x-axis, and we can see now it's actually going down. It's important to note that once again, your domain will stay the same. Your range, however, is going to almost be the exact opposite. Instead of going from 0 to infinity, we're going to be going from negative infinity to 0 for our range of the function. All right, and for our last variable, I call this one c. It's what we were doing to our x variable. So instead of 2 to the x, we're going to have 2 to the x minus 1 or 2 to the x plus 1, and we're going to see how that changes our graph. All right, for our first comparison, we're going to have 2 to the x plus 1, and we're going to compare that to 2 to the x. Again, our blue function is the parent function, so we have 2 to the x here. And then 2 to the x plus 1, we can see has been shifted to the left 1. And so similarly to what we've done in the past, because we are affecting our x variable directly, we're going to be doing the opposite of what it says. So it is x plus 1, but that's going to be a shift to the left 1. For this function, though, important to note, your domain and your range are going to stay the same. So a horizontal shift is not going to affect either one of those. To finish off our transformations, we're now going to be comparing 2 to the x minus 1 with our function. So we can see again, 2 to the x is our blue function. Our new function, 2 to the x minus 1, is shifted to the right. And that follows a pattern. Because we have 2 to the x minus 1, we're going to do the opposite of that negative 1, and instead we're going to be moving to the right one. And again, we can see the domain and the range have not changed based off of a horizontal shift. All right, we're going to go ahead and compare our functions with 2 to the x to describe the transformation. To begin with, we're going to look at a negative 2 to the x plus 3. And there are two main differences. Instead of a positive 2, we have a negative 2. And I called that my a value. And that's going to reflect over the x-axis. For our second difference, we have this plus 3, and that is what I call my b value, and that plus 3 is going to take the whole function, and it's going to move it up 3. So those are two different transformations when comparing negative 2 to the x plus 3 to a 2 to the x. For our second function, we're going to go ahead and compare 2 to the x plus 2 minus 1. So this plus 2 I called my c variable, and that is going to be affecting it by a horizontal shift. Because it is a plus 2, we're actually going to go to the left 2. And then for that negative 1, again, that was what I called my b value. That's going to take it down by 1. And those are the descriptions of our transformations when comparing the new functions to the original. All right, in addition to our transformations, we want to identify some other things that will help us graph. So we can find some y-intercepts. To find the y-intercept, what we're going to do is we're going to simply plug in 0 for x and simplify. And whatever we get as a final answer is the value of our y-intercept. All right, we're going to go ahead and find our y-intercepts for these first two examples. Again, we're going to be plugging in 0 for x. So my first expression is going to be negative 2 to the 0 plus 3. And something that is very important to note here is it is not the quantity negative 2 to the 0. It is negative 2 to the 0. And I know it's like that because otherwise we would initially have our exponents around the negative sign. So 2 to the 0 is 1, but this is going to end up being a negative 1 plus 3, which gives us a positive 2. So my y-intercept then is going to be 0, 2. Again, because I plugged in 0 for x and I got out 2. Okay, we're going to do the same thing to find the y-intercept for our second function. We're going to go ahead and plug in 0 for x, which means I have negative 4 to the 5th minus 3. If I simplify negative 4 to the 5th, we get negative 10 24. And then when I subtract 3, we get negative 1027, which means well, y-intercept for this function is going to be 0 and then negative 1027. For our asymptotes, the graph f of x equals a to the x plus b has no vertical asymptotes. So we never have to look out for those or identify those. However, our same function is going to have a horizontal asymptote at y equals b. And we discussed this in the initial setup when we were talking about our vertical shifts, how that plus or minus definitely affected the horizontal asymptote. It was also part of our range. So that is definitely a relationship where whatever we're adding, subtracting is always going to end up being our horizontal asymptote. Okay, just to verify that we can apply that, we want to make sure we can find our horizontal asymptotes for these functions. All we really need to do is identify the number being added or subtracted. So for our first example, notice we were adding 4, which means we're going to have y equals 4 as our horizontal asymptote. For our next example, we are subtracting 7 from the function. So I can simply say that y is equal to negative 4 is going to be our asymptote. And then for our last one, there is no number out here. So we can assume that is a plus 0, which means that your horizontal asymptote is going to be y equals 0. All right, we have a special exponential function, and its f of x is equal to e to the x. This is going to have all of the exact same transformations as our a to the x plus b, because again, it is another exponential function. It's just a very special one. And one of the uses for this is it's definitely used when we're trying to find compound interest or anything where we're earning interest for bank accounts. Here we can see the general shape of our function e to the x, and I've included a table of values here for your reference to make sure our graph is consistent. But you can see it is a general exponential function that is increasing. As you go from left to right, it is going up. We have the same domain value of all real values. We have the same initial y-intercept of 0, 1, and we have the same range of 0 to infinity. So it all checks out with just being another exponential growth function. All right, to end our lesson, we're going to have a couple examples talking about compound interest. And to do those problems, we have a formula. Our formula is a equals to p times the quantity 1 plus r over n to the nt power. Each one of our variables represents something. So to begin with, a is going to be the ending balance, or what we're trying to obtain. R is your interest rate, and something that's very important is you always need to convert that to a decimal value, so don't forget that. P is going to be your principal or your starting amount. T represents time, and it is always in years. So if you're ever giving a time value that is not in years, you have to first convert it. For example, if we're doing something for 6 months, that would be half of a year. And last but not least, n is the number of times something is compounded in a year. For example, if something is done semi-annually, it's going to be twice a year. If something is done quarterly, it'll be 4 times a year. If something is done monthly, it's 12 times a year. So we have to take those number of times something is compounded and translate into the number of times a year that it happens. All right, for our first example, we have a sum of $10,000 that's going to be invested at an annual interest of 5% compounded quarterly. Find the balance after 4 years. So our first task is to identify the variables within the context of the problem. Because you know that we have a sum of $10,000 that's invested, that is your initial amount, so that's going to be your p-value. We know it's going to be going for an interest rate of 5%, so we know r is going to be that, but we have to convert that to a decimal first, so 0.05. It's compounded quarterly, which means it's going to happen 4 times a year, and it's find the balance after 4 years. So that means that t is equal to 4. Since we're trying to find the balance, we know that we are looking for our a value. So let's go ahead and plug it into our formula. We would get 10,000 times 1 plus 0.05 over 4 raised to the, I'm going to go ahead and multiply my two values together, the n and the t, to get 16, just to make sure I don't have any mistakes when I'm calculating this. Okay, so now all we have to do is put this into our calculator. And if we do this correctly, we get approximately $12,198.9. For our next example, we're going to go ahead and compare different types of compound accounts. We're going to compare quarterly with monthly. So let's go ahead and identify our variables from the problem. We have a total of $6,000, so that's going to be your p-value. It's going to be interest rate of 6.5%, so we know r is going to be 0.065. And you want to find the balance after 3 years, so that means t is going to be 3. For the quarterly account, that's going to give us our n value. So I'm going to say n is going to be 4. And then for the monthly one, n is going to be 12. So we're going to go ahead and set up our problem and again compare what we get as our answers. For part A, we have 6,000 times 1 plus 0.065 over 4 and then raised to the 12th power. Again, I went ahead and I multiplied my n and my t value together just to make sure I don't have any calculating mistakes. For B, very, very similar. We have 6,000 times 1 plus 0.065. This time it's going to be divided by 12. And then for my exponent, it's going to be 36 because I multiplied my 12 and my 3 together. Okay, so when we calculate our answer for A, I got approximately 7,280.45. And then for my next example, I got approximately 7,288.03. So notice that if we compounded things monthly, our value is slightly more than if we compounded things quarterly, and generally that's going to be true. The more you compound something, the more often interest is added, and the higher value you're going to have. All right, for our final compound problems, we're going to be talking about what happens if we compound something continuously. And if we do that, we actually have a different equation. We have A is equal to PE to the RT power, where P is again going to be your principal, R is again your interest rate, T is time, and A is balance. And notice that we have an E here. And this E is approximately 2.71. So if you can find E on your calculator, you can use that to approximate it. But we want to be as accurate as we can. So when calculating these problems, we're going to try and identify E in your calculator to use that instead of the approximation. Let's go ahead and finish our problem. Okay, so just like before, we're going to try and identify our variables from our problem. So we have a sum of $10,000 that's going to be invested at an annual interest rate of 5% compounded continuously. It's very important that we see that word continuously because it automatically denotes to use this equation as opposed to the other one we talked about. And we're going to find the balance after 4 years. Okay, so from our variables, I know that P is going to be 10,000. I know that R is going to be 0.05 because again, convert that to a decimal. And I know that T is equal to 4 because we're doing this for 4 years. When I plug this into my equation, I get 10,000 E raised to the 0.05 times 4. And I'm going to go ahead and simplify that real fast. And I get 10,000 E to the 0.2. Okay, I'm going to go ahead and plug this into my calculator. And again, I encourage you to try and figure out where E is on your calculator so you can do this exactly as it says and not approximate with 2.71. All right, if you find E on your calculator and you get this done correctly, then you should get the answer of, $12,214.03. All right, guys, that go ahead and does it for our lesson today. Go ahead and get started with the homework, and good luck.